Okay, let us now take a look at the Gaussian distribution. A Gaussian distribution sometimes is also called a bell curve. I'm sure you have seen that somewhere. And that's a continuous probability distribution. Before we get into the specifics of a Gaussian distribution, let's refresh what we've seen on the discrete side. Discrete side, we had a sample space, omega, yeah? And the sample space was the aggregate of all the possible outcomes of an experiment. Yeah. Now then, we map this sample space to R, the real numbers, because we want to be able to do calculations. Yeah. And this we call the random variable. In this case, a discrete random variable, and basically what it does is it maps your sample space to R. Then a discrete random variable has a probability distribution, and in the discrete case we call this PMF, probability mass function. Yeah. What does this Px give? Px is the probability that the random variable equals head or tail. Yeah. It gives the probability of occurrence of the possible outcomes of an experiment. So here I have an experiment. I had 4 coin tosses, 2 heads, 2 tails. The probability of occurrence for head was 2 because I saw 2. The probability for tail was also 2. It is clear that if you want the probability of these 4 things happening, that this probability is 1. Yeah? That's first thing to notice. Now if we go from discrete to continuous space, basically what happens is that our sums become integrals. You know, an integral is a stretched sum. It's an S from sum. And here in the continuous case, we work with a sample space and an event A that is a surface. So there's no probabilities in specific points anymore. Yeah? So the probability of x equal to A is 0. But the probability of x being between A and B is actually the surface of this thing. Yeah? So is the integral from A to B. And the probability mass function, in continuous case we call probability density function. Yeah? Here mass function, because of these points, could be seen as masses. Remember, the expected value could be seen as the center of gravity. While in the continuous case, we look at surfaces. So that is f of x dx. Yeah? So f of x is your PDF. Now it's also true that if you take the integral of f of x, yeah, from minus infinity to plus infinity, that must be 1. It's exactly what we did here. Yeah? But we replace the sum by an integral. Okay. Let's take a look at the expected value. The expected value of a random variable x is again going to be a sum of f of x times x dx. Yeah? Is exactly the same as in the discrete, but the sum becomes an integral. And the variance of x, yeah, equals, we call it sigma x squared, equals, again, integral of x minus the expectation of x squared f of x dx. Okay, that's the variance. So now let's go and take a deeper look at the Gaussian distribution.